based upon this concept of Bohr's model. So I'll show you Bohr's model again, but it's much more in depth than just Bohr's model. So if we do Bohr's model, we know that we have different energy levels. Okay, we got E1, E2, and E3. So if the electron's in E1, what do we know about the state in which the atom is at? Ground level, the ground state, the lowest energy level. And if it kicks up to E2, we know it's in a excited state, right? Because that's not its normal energy level, and then that would drop back down, and then we get certain waves of light out. And you guys did the flame test, and you guys kind of see some of that, right? You've seen some of the different colors. Now, if you would break that flame down with a spectroscope, then you would get individual lines like that. So if we had a spectroscope that we were looking through, we would get, for example, sodium is up here, and if you notice, it just has two yellow lines. So sodium was kind of a yellowish orange. But the only thing sodium has is two yellow lines. Okay? You guys also have potassium. Potassium was kind of this color here. Okay? It was kind of a reddish orange, wasn't it? Salmon color type of deal. So if you look at potassium, it has the kind of a reddish orange, and then you go all the way over and it has a little bit of violet in it over on that side. So you have a combination of violet and red, and that's why that one's hard to identify sometimes. Because sometimes people think it's purple and violet, and sometimes they think it's, kind of the reddish end. But if you look through a spectroscope, you get those lines every single time. So they're kind of like a fingerprint for the particular elements that we have. And what creates those lines are these electrons, and they're moving. And they're creating those energies that are coming off. And there's more than one that it creates. So that's Bohr's model. Now we're going to adapt this model a little bit and change it. Okay? And it's called the quantum theory. We're going to look at what's called the quantum has to do with quantum size. Quantum is a specific amount of energy that's lost or gained, or a specific amount of energy that the electron has within the atom. So it's called the quantum theory. And I'm going to give you 4 parts to it. It's hard to understand this until you see all 4 parts and how they work together. Okay, so every electron will have a way to identify where it's at by this theory. It will tell you a little bit about the energy it has. They take on different shapes. The electrons don't have a nice little orbit around the nucleus like this. They don't have that. They're not going to be at any particular spot. We call electron cloud is what we're going to call it. And they have different spins. Okay, just like the Earth has a spin when it's going around the sun, right? It has a spin and gives us our 24-hour day, right? But it's also what? Moving around at the same time, revolving around the sun at the same time. So it's doing a couple things. These electrons are doing the same thing. They are moving around the nucleus, but they also have what's called an internal spin. They're moving. Okay? It's either going to be one direction or the opposite direction. Okay? Going to be. So we need to talk about the spin that they'll have. So what I'm going to introduce you to is some symbols that represent these quantum numbers. There's 4 quantum numbers in the quantum theory that we're going to visit and talk about. Okay? So this is where your notes should begin. This is called the quantum theory. There's a lot of people that had input into this, and this guy named Schrodinger, he came up with, you guys ever heard of Schrodinger's cat?
Yes.
Yeah.
Is that the one where it's like cats in
Oh, the box.
Yeah.
Something about it. You never know if it's alive or dead. Like you, I don't know.
Right.
Oh, yeah.
Right. Or right. So Schrodinger's cat has kind of come up with the idea of not knowing the specific location of an electron at any point in time. Okay? And I don't know all the ins and outs of Schrodinger's cat, but that's kind of where that name kind of come from. All right? Now, if you ever watch Big Bang Theory, they will actually, at different times on their whiteboard, they'll do different things, and they'll have some of the quantum theory up there and some of the symbols and numbers associated with it. You know, you can kind of look at that at times. And probably should find an episode that has that, so I can kind of show you that, you know, they do have scientists that will probably help with, you know, going through that process and make it a little bit more legitimate. So we have 4 parts. All right, and these 4 parts indicate the energy and location. Energy, location, and behavior of the electron. We'll say each electron in an atom. All right. So these parts actually can be plugged into a mathematical equation. So this is really a mathematical equation that they come up with, and these symbols and numbers actually, if we go more in depth into it, they'd be the actual numbers that we would plug in, but we're not going to go that far. So the number one thing, the most important part, is called the principal quantum number. So these all end in quantum number. Now, some of them aren't numbers. Okay, we could give you the number and rationale for that, but we're not going to. It's symbolized as, when you see it in there, it'll be symbolized as a N. So like in math, you can say, like in math, you might say P equals 1, or D equals minus 3. Then you go through, or D equals minus 5, it changes, okay? So this one's going to be N, and it's going to be whole numbers 1 through infinity, okay? If you had enough electrons to identify, okay? So I'm just going to go, they're going to be numbers like 1, 2, 3, ... Okay? They're whole numbers, okay? And so what they do is they indicate the location of the electron away from the nucleus. Okay? They do a couple things. All right? They indicate the, we'll say shell, where the electron is located. And they also help us determine how many electrons are in that shell. Okay, it's getting down a little bit farther. You guys see that? Do I need to raise it up? I don't know if I do, then it'll change my, but I will raise it up. Okay? I need to go through and readjust it though. Uh-oh. I can't see my... Oh, lucky. Got that one. Okay. All right. Now, how does it determine the number of electrons in a shell? First of all, kind of give you an idea. It's kind of like Bohr's model. We're going to use Bohr's model to identify these energy levels. Okay. So that's what we're going to do. We're going to identify Bohr's model. And Bohr's model kind of allow us to kind of see these energy levels. Okay. So we'll call this shell or energy level 1. So the book will say energy level 1, shell number 1. So I'm going to use shell. Can you think of shells? You play a game where there's inner shells, and you guys ever see those Easter eggs? Where they have, take them apart, there's another Easter egg, take it apart, another Easter egg. Okay, so think of that. These are all the shells. And so this would be shell number 1. This is shell number 2, shell number 3, and so on and so forth. They keep going. Okay? So, first thing it does, if I say shell number 1, that's the principal energy level. The electron's here. If I say shell number 2, the electron is farther away. If I say shell 3, 4, 5, 6, 7, they just get farther away from the nucleus. What happens to the size of the atom when I have electrons in 3 versus 2? What happens to the size? Bigger, right? So if I have electrons just in energy level 1, that's a small atom in relationship to other atoms where you have electrons in shell number 2 and shell number 3. So what happens is these shells fill up with electrons. And the first shell will fill up when you have 2 electrons in it. You guys remember when you guys learned a little bit, they'll say the first energy level has 2 electrons. And if you look at the periodic table, how many elements are in the first period across the periodic table? 2. Hydrogen and helium, right? Then the next period you go across, how many do you count? 8. Well, that's how many's in the second shell. So the first shell will have 2, the second shell will have 8. The third shell, you can't go across the third row, you have to go across the fourth row to determine how many's in the third shell. And I'm going to explain why that's the case a little bit later, not right now. So how many would be in the third shell? 18. Now, the fourth shell would have more than 18, and you'd have to start at element 55 and go all the way across that row, including these where cerium or the lanthanide series go through there. So if you count across there, how many do you have? So you got to count across the 18 plus that other row. 32. So it goes 2, 8, 18, 32. Okay, and then we don't go any higher than that because we'll run out of electrons.
Is that in every atom?
No, that is not in every atom. For example, hydrogen will only have 1 electron here. That's it. But the possibility is if you fill each shell, then they have 2, 8, 18, 32, so on and so forth. Okay? So how does that principal quantum number help you determine electrons in a shell? Okay? Well, first of all, I'm going to show you a formula for that. So I'm going to go ahead and say number of electrons in a shell is a basic formula. Okay? And that's going to be 2n squared. So the principal quantum number is 2n squared. So if I say free, how many electrons are in the third shell, you can either memorize it or you can go, oh, I don't remember that. So what would you do? You go free squared times 2. How many? 18. Now if we had a fifth shell that would fill all the way, we don't. The fifth shell can't because we'll run out of electrons. We don't have an unlimited supply of electrons. But if we had a fifth shell, how many electrons would fill that fifth shell? 50. Make sense? So, first shell, 1 squared is 1 times 2, 2 electrons. Second shell, 2 squared, 4, 8. So, at any time, I can determine how many electrons are in a particular shell. Okay? Any questions you have with that? We're going to build upon that. So, the principal quantum number is a location where the electron's at. Kind of like his address, Austin. He's in Beatrice. The mail will get delivered to the Beatrice post office. Okay? So that's, it's in the state of Nebraska, we're in Beatrice. Okay? And so it's the most important part, first part of knowing where the electron's at. All right, so that part's done. Then we get a little bit more, we talk a little bit more about energy that we're going to have. And when we take a look at quantum numbers, we've got the principal quantum number. The next one we have is going to be, I believe, the angular momentum quantum number. Okay, I'm going to write that down here in a second. And then we'll talk about what that symbol represents and how it works. It's called angular momentum quantum number. Okay, now, this one we're not going to give a number because it can be a negative integers and positive integers, including 0. Okay. In AP chemistry, we don't even do it anymore. We used to see, well, how many possible numbers could be? And it could be like -2, -1, 0, 1, and 2. Okay, or it could be -1, 0, or +1. And so we're not going to go to that extent. So what we're going to do, that's symbolized by an L. Okay? That's how that symbolizes. And what does that do? What does that say? Well, it indicates the shape that the electron takes as it revolves around the nucleus. Okay? Okay, so here's the deal. There's an electron. Every electron has different shapes it can take, and it's moving around the nucleus. So this is kind of brand new. We know about energy levels. The farther you get away, more energy that they have. We can have more electrons and energy levels or shells that are farther away. So this indicates the shape of the electron. There are 4 major shapes that we're going to give you. That shape also indicates energy that it has within the shell. So we have these different we would call them subshells within the shell. So we have a shell, and then we can possibly have different shapes the electrons take within the shell. And those shapes are indicated. We have shapes that are indicated or subshells. So this is where we get a little bit more complicated. And they are S, P, D, and F. They describe the shape of the shell. All right? Now, if you have your book, this is where your book comes in handy in showing the shells. Okay? If you turn over to page 108, we're going to show you the subshells. Okay? Turn to page 108. So, let's look at the first two. We got principal energy level. This tells where the electron's at, what shell it's at in, and it also indicates how many electrons can fill the shell if we use that formula 2n squared. All right? The angular momentum quantum number indicated with an L. If L equals S, now that we would actually give that a number. We give it a 0 number if we were learning the numbers along with the symbols. So if we said if L equals S, that would be L equals 0 would be an S. If L equals P, P would be a 1. If L equals D, that would be a 2, and so on and so forth. But we're not going to do the 0, 1, 2, 3, 4. Okay? We're just going to say S shape. Now the S shape is just a spherical orbital. Okay? It's just kind of a cloud. If you guys look, you think of it as a sphere or a ball. Okay? That's the way that you're going to think of it. So, be like a balloon that's round. Okay? That would be an example indicating that shape. Okay, like that. All right, so that's the shape. It can be anywhere in that, where that surface is at. Okay? If this is really a thick balloon, if we had one that was really thick, then it could be anywhere within that thickness where the electron's located. Does that make sense? Okay, that's the first one. That's the lowest energy subshell. Okay? A P, in your book, you guys see what a P looks like? Looks like a dumbbell, right? So a dumbbell shape, we like to have visuals. In the book, they don't really do it justice because you don't see the three-dimensional view. Okay, so that's a P. All right, so I'll go ahead and draw that. But a P is, and then I won't do D or F. We don't need to go to that extent. So then a P would look kind of like a dumbbell shape. And this is the second lowest energy subshell. And you can kind of keep going. D is going to be the third, and F is going to be the fourth. Okay, so these are just shapes that the electrons take in the pathway around the nucleus. Okay? Any questions with that? Within each subshell, Total electrons, I'm going to go ahead and share you with that, the formula for that. So I can share you with the formula within each subshell, how many electrons can fit that subshell. Okay? And yeah, I think I'm going to wait on that because I need to introduce the third one before I do that. Okay? We'll revisit this because the next one is, when we take a look at it, it's called the magnetic quantum number. Okay? So we're going to introduce you to that one. Okay, so the magnetic quantum number is symbolized with a little m. And it indicates the orientation of the electron. I'll need to explain what that means. This will be the last one we'll talk about. We're not going to get into spin. Spin's pretty easy compared to the rest of them, but we need to talk a little bit about right. So the different orientation could be a pathway. So we can say pathways as well. Maybe that will help understand. So. The S has one orientation or one pathway possible. That's it. The P has how many? 3. Same shape, but 3 different pathways it can go. The D, guys, give me a pattern here. What do you think the D is? 5. And the F is 7. And if we have a G, which we don't, because theoretically if we get to where we build more and more atoms, theoretically it would keep going, and the G would have what? 9. Right? So it's odd numbers. Okay? Last thing I'm going to give you is that within a pathway that we can have, it tells us how, if we do use this formula, we can get the pathways. So if we do n squared, that tells us how many pathways we have. Nope, we'll do that. Don't write that down. Okay? Hey, good job. I know it's a little fuzzy right now, but we'll build upon that Tuesday.